I get into the meat of the matter, I wanted to describe just a little bit more my personal path and how I ended up studying computer vision in Europe. So as Adafi mentioned, after I finished studying at St. Joseph's Convent, St. Joseph, I decided to study electrical engineering at Princeton University. While I was there, I was at a student exchange program. So I went to Oxford University for 1 year. And while I was there, I was introduced to, to the field of robotics, computer vision, artificial intelligence in general. So I found it extremely exciting. And then when I went back to Princeton, I decided to do what is called a certificate, or you can say a minor, in robotics and intelligent systems. And so I graduated with this minor. However, I didn't go directly into this. It was something that I was interested in, but I wasn't necessarily sure I wanted to study this for a career. Actually, I ended up going into the finance sector after I graduated, which is a very typical path for a lot of people who do STEM, right? Very often, a lot of people do STEM, but then they somehow find themselves doing finance just because it's a very obvious path, it's very easy, it's very lucrative. But when I was there, I was not motivated. It was really very boring, very simplistic things, and I found myself, during the days just going on Wikipedia, reading about physics problems and things like this, because it was just not really interesting looking at spreadsheets all day. So then when the opportunity came, I found out about a PhD program because I had actually inquired the year before, but I hadn't gone through with it. And then this came into my lap, and I thought, what could be more fun than going to Barcelona for 4 years and being paid to just study, to look at images and really understand them. So I told myself, okay, I have time in my life, finance is always there. So I went to Barcelona for 4 years. And then while I was there, I ended up doing an internship in France. And this internship was with Xerox. I had a really wonderful time there. And so when I graduated from my PhD, I had the opportunity to go back to be a permanent researcher there. So then I ended up being a researcher in France, in Xerox. And actually, my lab was acquired by NEVA, which is how I am currently working at NEVA Labs Europe. There's NEVA, which is it's a South Korean company that is basically, you can call it the Google of South Korea. So basically their bread and butter is search, web search. Also they have a lot of mobile apps, and they work on autonomous driving, robotics, augmented reality, many of these fields. And so now this is where I'm working as of a few days ago, actually. So that's a bit of my story. So I can show you a brief video that lets you see a bit where I work.
Europe will contribute to this goal.
Oops, and I got rid of it.
Europe will contribute to this goal by developing new technologies that analyze environment and our activities, that can understand our intents and anticipate them, and that can interact with us in a natural, personalized and proactive fashion.
We're working on systems such as domain adaptation, which basically means you want a machine learning system to work in many different operating environments, maybe in different places, in different weather conditions. For instance, if you're talking about self-driving cars, you want them to be able to detect signs and traffic lights and road markings in many different places. But the big penalty of using machine learning methods, you have to collect lots and lots of labeled training data. And so in order to avoid collecting lots of data.
So that's just to give you a little taste of basically where I work, so you can see actually, this is actually the building that I spend all my days in, my working days, of course, not my weekends. Okay, so that's a little bit about that. So before I get into this, I want to mention that this is, we have an hour and a half together. I don't want it to be boring. So please, let's make it as interactive as possible. Any questions you have, feel free to put your hand up and ask, okay? No wrong questions. Let's make it as fun and as dynamic as we can. So here's what I want to talk about. First of all, to describe to you what really is computer vision and how does it relate to what we know, human vision and biological vision. Then also, what does computer vision aim to achieve? What are the problems that we try to solve in this field? Why is it a difficult problem? Why do we have to do research on this, right? Why is it not a completely mature technology? I'll describe this a bit. Also, how is it applied? So where do we see it in use every day? What are the current challenges? And there are many. And then I'll have a brief conclusion. So let's start with what is computer vision. So let's think of vision trying to understand visual content. So let's say we have an image or a video. What we're used to is having some sort of sensing device. So this could be the human eye, it can be the eye of an animal. It can be, for example, a webcam or a smartphone camera. Then we need to interpret it, because one thing is taking the image, another thing is understanding what the image is depicting, right? What is it really representing? Those are two separate things, and it's important to keep that in mind throughout the lecture. And so once we have a digital or some sort of internal representation of the image, we need to be able to interpret it. And for this, we also need a device, which is separate from the imaging device, okay? And for us, this is our brain. For a computer, this would be, the CPU or the GPU in your phone or your machine, okay? And once we can interpret the image that we have, we can come up with interpretations and understandings of the scene, okay? So for example, here, it's clear that this is a pond with a walking path across it. And one thing is to see that, but of course, we have a lot of additional information that we can infer from just this image, okay? So for example, we understand that this is a walking path. We can predict that maybe in the next 5 minutes, we would see somebody walking across the path. We would understand that maybe if a fish jumps out of the water, that makes sense. So there are a lot of things that we can understand about this world just from this image, okay? And this is something that's very effortless for us, but it's very difficult for a machine to be able to do that, okay? And this is something also to keep in mind throughout the lecture. So let's look a little bit at what computer vision is related to. So as you can imagine, it's a very multidisciplinary field. It involves a lot of insights from what we might call basic science. So things like physics. Physics is a very important part of computer vision, particularly in more traditional aspects of it, because it involves optics, right? The images that you take are really the result of a physical process of light hitting surfaces which absorb and reflect light in certain ways. And this is what you capture with an imaging device. So physics is very important. Biology, of course, is very important. Psychology as well, because as you'll see in the talk, a lot of vision involves the brain, right? And for this reason, a lot of things that we see that we take of as for granted or that have to be real are actually very subjective. Vision is subjective. We don't all see the same things. And this is why psychology is important. It also involves robotics. It also interacts a lot with the field of robotics, information retrieval, graphics, and many others. So let's look a bit at biological vision, right? Where the sensing device is our eye and the interpreting device is our brain. So human beings, compared to a machine, human beings are exceptionally good at visual perception and understanding. We see effortlessly. The way we might have to think about how to solve a mathematics problem, we don't think about how to solve the problem of what are we seeing, what does it mean, right? This is something we don't think about. It's completely effortless, but it involves a lot of computation that we're not conscious of. It's like breathing for us, right? We don't think about it. As I say here, we use 70% of our brain processing power for visual processing. When you think about it, if you think about the amount of data that it takes to send a video or to send an image over a smartphone or something like that, you know that it takes a lot of megabytes. If you imagine yourself taking a video, a smartphone, and just filming everything all day, imagine how much data that stores on your smartphone. You can't even keep that. And think about the fact that right now we're just processing that vast amount of information every time we open our eyes. It really is a lot of processing that's required. So how would you describe this image? Anybody? No wrong answers. Just what comes to your mind when you see this image? How would you describe it to me if I wasn't seeing it? Sorry? Yeah, more? Anything else? Ah, okay. Is there any way to take the light down a little bit? Anybody see anything? Does anybody see it okay, or is everybody not seeing the image at all? Is that? Okay, thank you. So now, somebody describe the scene in one sentence. Anybody? Sorry? All Europe, thank you. Anything else? Easy? Busy, thank you. Anything else? Vintage, okay. So you all can tell that, okay, it looks like it's sort of a European city. It has a vintage look to it because of the color. I'm sure you guys probably look so obvious, so you don't even want to tell me, but you see that there are people there, right? I know that's so obvious, but trust me, having a computer tell you how many people are there is incredibly difficult, okay? But it's something you don't even want to tell me because you think it's so obvious, okay? You can also tell there's a street there. You can tell that we're looking down the street. You can tell that there are buildings. You can tell that the people that are in the background are not tiny people. You can tell that they're just people that you're seeing at a distance, right? You understand that, right? You know they're not just tiny humans, okay? That is not trivial at all, and we don't even think about how obvious that is to us. Right? So we perceive this as a 3D scene. We understand depth. We understand this person is close, people are behind. All of this we understand just instinctively. And that's even though we have very little information. We really just have a 2D projection onto this screen, and from that we can have a vast amount of information. So look at this. This is a very blurry, low-quality image. Can you tell me anything about this image? Right. You're seeing 2 to 4 people, right? Anything else? Colors. One person. Put up your hand. Okay, but you all got a lot, right? You all can tell that there are 2 to 4 people in this image. You could probably tell that maybe one is a woman, that there's a man. And if you look, this is very little information, but you all are all very confident about that. What about this example? What do you see? Anybody? Somebody put up their hand? Sorry, let's just... Thank you. A man at a computer desk. Right? Very obvious. But there's very little information that you have there. But we have a lot of innate knowledge and a lot of experience that allows us to understand this very quickly. So human vision is very powerful, as I hope I've just described to you, right? It's very obvious, it's effortless. But it's also, as I said, it's subjective. It's not an objective thing, and it's deceptive. So we perceive the visual world as something external, right? We don't see it as something that's in our heads. We see it as something that's around us. But that's not true. What I am seeing right now is in my head, okay? It sounds a bit weird, but it's true, right? We don't actually, what I'm understanding from what I'm seeing right now is really something that's been processed by my brain. Right? So human vision, because of that, it's subject to illusions. It can be tricked. And I'll show you some examples in a second. It's quantitatively imprecise. It's limited to quite a narrow range of frequencies of illumination. I'll discuss this a bit as well. And it's also passive. So I'll describe all of these in a bit. So let's look at a very standard visual illusion. So just to pause here, I want to be just, as it says, the 2 squares that you see, do they look like the same color to you? But they are, right? And you'll see it in a second. So why is this happening? This is a very standard, very famous, well-known visual illusion that was created by Professor Adelson from MIT. And so this is one example of vision tricking us. Because we're seeing a checkerboard pattern, if you introduce one square that does not fit the pattern, we will tell ourselves that because of the shadow from this cylinder, the shadow is causing this change in brightness, but not the color itself. So this is a very standard visual illusion that you can see replicated in many other types of experiments. So here are some other examples, very well-known ones. So for example, Do these two lines look the same length to you? Who says yes? Put up your hands. Okay, and who says no? Okay, so the no's are wrong, but it's okay. To my eyes, I know that the two lengths are the same. I know that they're the same, but they do not look the same to me. This one definitely looks longer to me, but it's not. Okay? And for example, these lines, do they look parallel to you or do they look bent? I shouldn't say parallel. Do they look straight or do they look bent, these ones? Who says bent? Okay. They look completely bent to me, but they are straight lines. And for example, if you look at these at the corners here, do you start to see any white spots that follow? Right. You can tell that that's not there, right? Because they change every time you look at a different spot. Right? All of these are very standard visual illusions. Okay? This is another example. I like this one a lot because these lines are all parallel. All the diagonal lines you see here are parallel, but they look completely non-parallel, right? There's so many of these. I can go on for a long time. So here's another one. This is with respect to color. So if you look at this first visual stimulus here, you can see, do you see these 4 bars? Number 1, number 2, number 3, and number 4? Would you say that these 4 bars have the same color or have different colors? Who says different color? A few people. So for me, they look fairly different. It might not be so easy to see here, but they are the same. So you see, if you take this line, you pass it through, you see that the color does look exactly the same as what it surrounds, right? These are other examples. Do these 4 bars look the same color to you or different? Who says different? Almost everybody, right? They're exactly the same color. These are all the same color. They only look different because of what they're surrounded by, okay? So if you see here, this bar is surrounded by red, and it kind of has a more yellow look. This one is surrounded by blue, and it has a more blue look. And that's the only reason why it looks different. And the same thing here. So this line looks a little different depending on how far you go, only because of what the colors it's surrounded by. So these are all very standard visual illusions. Does anybody see anything strange about this image? One person tell me. Put up your hand. It looks like it's moving, right? I showed it to my mother this morning, and she didn't believe me. But you all are seeing this, right? That is totally not moving at all. That is just our brains having a very bizarre signal that is just confounding our visual processing, and we don't know what to do with it, right? So we're just seeing these very strange hallucinatory movements that are not there. And here's another one you might be familiar with. So color constancy is this property where basically an object has the same color to us. We perceive it as the same color under different lighting, right? So for example, you're seeing these marbles. What color do you think this marble is? Anybody? Any one person? Clear, right? More or less. You wouldn't say this is a yellow marble, right? But the reason why you wouldn't say that is because everything looks kind of yellow, right? So you tell yourself, your brain is subtracting the yellow. Because your brain is telling yourself, okay, it's just a yellow light. It's not actually yellow, it's white, right? But it's giving a kind of a yellow hue, but it's not the color of the actual object. But this also tricks us. This is a very useful property in many situations, right? But it can cause issues. Who remembers this example? Anybody remembers this? Yes. You all remember this issue, right? Yes. This is exactly it. Who thought it was white and gold? Who sees right now that this is white and gold? Anybody sees this as white and gold? Okay, who sees it as blue and black? But some people see it as white and gold, right? When I first saw this, I was convinced it was white and gold, but it's actually a blue and black dress. Yeah? This is a perfect example of color constancy. So this is one visual illusion that everybody was very familiar with. And then here's one last one.
In interpreting the visual image, the brain...
So just to introduce, so this is Professor Ramachandran, who's a neuroscientist, a very well-known neuroscientist.
has to resolve ambiguities. And in doing so, it uses all sorts of assumptions, built-in assumptions about the world. And because it uses all these assumptions, which we can investigate in the laboratory and discover, you can also trick the visual system. And this is what you call a visual illusion. This is the M's room. It's a grotesquely deformed trapezoidal room. But the astonishing thing is, if you look inside the room looks completely normal. And the walls look parallel and everything seems fine. The reason is that the brain has a built-in assumption that the walls of rooms are usually parallel. This is something we've grown up with all our lives. And this assumption is so strong that it completely overrides the fact that people are actually changing sizes. Even though in the real world, obviously people don't change sizes like balloons, here you're willing to see that because the assumption of parallel walls is much stronger.
So isn't it so hard to override that? I mean, you know that that person is not that tiny, but your brain can't let you really switch, right? You see it as a small person rather than somebody who's far away, right? And this is another instance of, as much as we know what something is real, our brain cannot, our perception doesn't allow us to see that. So that's vision, right? It's, as I said before, it's very powerful, it's very effortless, but it's not perfect either. And one last thing is that it's passive. So our vision, our perception, at least our visual perception, is dependent on external light sources, right? So whereas, for example, a bat can release sort of a wave, like sonic radiation, and get a feedback from that, and from that understand where obstacles, where people in its path, we rely on external sensors, right? So we rely on the sunlight or lamps or things like this. And one last thing I want to mention was, as I mentioned before, the spectral limitation. So we see this visible light, but that does not mean that that's the only thing that one can see, okay? There's a lot of information at other wavelengths of light. For example, this is the spectrum of the sun's energy that's radiated, at least like electromagnetic energy. And you can see that there's a lot of energy beyond the visual spectrum, right? So there's UV and things that are lower than that. There's infrared and wavelengths that are higher than that. But we don't see that, right? We only see the certain parts, which makes sense because if you look at the profile, you can see that the radiation is most active, is most strong in the visual spectrum. That means that we're being sort of efficient in terms of where do we spend our time trying to extract information. But it still shows that there's a lot of information that we do not gather, that, for example, a computer vision algorithm with a certain sensor can gather. So that is vision and computer vision in a nutshell. So now I want to discuss what's the goals of computer vision. What do we want to do? So to put it in one slide, the aim is to bridge this gap between pixels and meaning. We don't have to bridge this gap. Or I should say we do it, but we don't need to think about it. It's something that's just done almost effortlessly, as I said, automatically. But for a computer, they have to really, we have to design algorithms to get computers to do the things that we would do effortlessly, okay? Because we see this and we just see it, right? We just see, you can tell that this is a train that broke through like a building. But what you give into a computer, when you give a computer a digital image, you're giving them an array, right? You're giving it an array of integer values. That's all you're giving it. And from this, a computer needs to understand that, okay, I'm seeing a train crashing out of a building, etc. So I'll go through a series of the types of problems that we want to solve. One is recognition, so what we call visual recognition or object recognition. And the idea here is to recognize objects and people and understand the interactions between them. So what does this mean concretely? Let's say you have an image here, right? There are many things you can say about this image. You can ask, is it true that there's a lamp in this image? Is it true that there's a lamp here? Where are the people in the image? Where are they located? And you can put a bounding box around them to localize them within the image. This might seem so trivial to you, but trust me, this is under current research activity, and it's not at all a solved problem. What are people doing, right? So here we can say there are people walking in this area. You might want to know the pose of the people. how are their limbs, how are their joints related in relation to each other. So identification, you might want to know not just, okay, there's a building in the background, but I want to identify it. I want to know, what is this building? Is it a part of the Great Wall of China, for example? You might just want to give a general gist of the scene. You might want to be able to just have a caption saying that this is a scene depicting a crowded square somewhere in China. So another goal you might want to do beyond just sort of recognition and understanding is 3D understanding. So as I showed in one of the examples before, for us it's very obvious that we can tell what's up close to us, what's far away, okay? This is not easy for a computer vision machine to do. So basically we want to say, okay, given this RGB scene, somebody holding up their hands, I want the computer to tell me what's close and what's far, right? So for example, the red, so the warmer colors indicates closeness, and the blue, the cooler colors indicates being further away. And so these are the types of results you want an algorithm to be able to do. And you'll see applications of why these things are interesting later on in the talk. Okay, another one is understanding 3D models of objects. So you want to be able to say, I take some pictures of someone, of maybe the face of Forrest Gump, or I have let's say some frames from a video, and I want to use that to reconstruct a 3D model of his face or his head, okay? And why, we will see later on why these things are interesting. Another one is image enhancement. So let's imagine, you take a picture, like for some surveillance purposes of somebody's car, but you want to know, okay, the license plate isn't very well seen. You want to be able to enhance it to be able to get more information. You might also want to enhance images by sort of imagining. Because as I said in an example before, when you have images, very often we humans can fill in things, right? We might not see something might be hidden, occluded, but we have an idea of what will be behind it. So we want a computer vision algorithm to be able to do the same thing. So given this scene, you want the algorithm to say, okay, I know that here there will be a bit more road, it's the most likely thing, etc. Another example is this. So you might want to say, okay, I took a crappy picture of this scene. Could I have taken it without, this building occluding me? How can I remove this roof and put in something? This is what we call the problem of in-painting or image completion, to fill it in with something plausible. This is also something that human beings can do. We could have certainly imagined what would be behind this building, and we want a computer vision algorithm to do the same thing. Once again, any questions, stop me anytime. Just raise your hand. Okay, so these are I showed you some of the problems we try to tackle. Now, why are they difficult problems to tackle? So let's look at one very sort of narrow branch of computer vision, which is really related to understanding people in images and video. So say we have an image of people we want to be able to understand. To first of all, to detect them, to say where are people, are there anybody, if so, where are they? To recognize them potentially, to say, okay, I know there's a person, but who is it? Is it my mom, is it my dad, etc. To understand the pose, so not just know how they are, but how is their body, right? How is their limbs arranged? And to understand their actions and gestures, right? Are they doing something with their hands? Are they playing a sport? What type of sport, etc. So, but of course, people are very diverse, right? People are extremely diverse. They come in all sizes, all shapes, wearing all types of clothing that can be very loose, very tight, and things that are a bit, maybe, let's say, bizarre, okay? Also, people are very flexible. So you can never, something like this, we can understand this is a person in a very contorted position, but for a computer vision algorithm to understand that is very difficult. Also, as I said, there's a lot of occlusions. For example, if this person, if you don't see the legs, that doesn't mean we don't know there are legs there, right? We can understand that. But for a machine to be able to understand partially seen things is also very tricky. Another thing is faces. So we have to, for example, this is all the same person. You could probably tell, right? But for a computer vision algorithm to understand that, even if he's wearing glasses, if they have very different facial expressions, all of this complicates the problem dramatically for vision algorithms. And then also, as I said before, we use a lot of things beyond just what we see. We use our prior knowledge, We use our understanding of physics, our innate understanding of physics, how things operated with relation to each other, to tell us a lot more than what's actually there, right? So for example, can anybody tell me what they think this is? If you had to guess what object this is, anybody want to make a guess? One person? One person, put up their hand, I can't. Nobody? I heard a lot of mumbles just now. Yeah. Sorry? A boat? Okay, one option. Anybody else? Somebody over there had a hand up? Sorry? Okay, I got one boat. What about this one? A fish, okay. Anything else? Okay, so I got a boat and a fish, okay? Who wants to guess now the first one? Anybody? Everybody's in a car now, right? What about this one? Right. So you all understand now how much information context can give you, right? Boat and fish versus car, obvious, all of a sudden, and person, right? So this is something that we can tell because we understand global context, right? You can tell, okay, this looks like a building, it's looking like it might be a road, etc. But for a computer algorithm, for them to understand all that context, all it sees is an array, right? That's all it has. So we obviously have a big advantage because we can make a lot of inference about what things are likely, okay? Okay, so these are the challenges, and you know, I've shown you the problems. Now I'm going to describe basically why are we interested in computer vision, right? I've described to you what it is, why it's difficult, but now I want to show you how we can use it. So first of all, why should we care? Well, because, you know, vision is everywhere, right? Images, videos is really one of the most, I would say, most popular media for communication, right? All of us are familiar with social media, with Instagram, with Facebook, with Twitter, with all of these things. All these social media platforms really have vision as a major element of it, right? And YouTube as well, Flickr, etc. We are sharing and looking at videos and images all day long, almost. So here I'm going to go through with you some applications of where computer vision is being used right now. So this first one is Google Earth. So many of you might be familiar with Google Earth, Street View, things like this, right? So a lot of this involves computer vision. So in this case, I'm showing an example of a model, a 3D model of, I think this is the city of Seattle. And so this was created by taking 2D images, okay? And from these 2D images, creating a 3D model of the city. And this is what computer vision can do. So once you have this model, you as somebody can explore the city virtually by using images, many images that people took of it on their vacation, and maybe from a satellite, and you can take all of these visual sources together and reconstruct an actual place or even things. I mean, you can do this with objects as well. So this actually is an example. So here, let's say you have this face and you want to be able to model it in 3D. What can this do for you? So once you have a model of a face, you can use this face, you can use this model and transport it onto another face, okay? And this is what's done all the time for, let's say, special effects, okay? So let's say, for example, you have an actor and you want to transport the movements of his face onto something else. It's very typical, for example, in cartoons or animated movies. So let's say you have Shrek. Shrek, his facial movements is actually done by an actor, right? So what they do is they have a model of the face of Shrek that they do in some sort of 3D graphic software. They take the model of the face, and when the person makes certain facial movements, they simply just transport it, map it onto the 3D model of Shrek or of anything else, okay? And this is a straight application of computer vision. And this is the same thing. So this is another example of basically Pirates of the Caribbean, where the actual actor, you see he's there with markers on his head. So these are actually markers that are recording movements on his face. But computer vision can allow you to do that automatically. So you don't have to put these physical things to record how are the muscles moving. You can simply look at it and then from that analyze, okay, how are the lips moving, how is the eyebrow moving, etc. Another application, one that I think is very well known by now, is face detection and recognition. I'm sure most of you have used by now a smartphone or a camera which already automatically recognizes where are the faces, right? So this is, of course, this is computer vision. It's a very old problem that we've been looking at for a very long time. And it's still not solved. It's solved in many cases where you have a frontal face, so nobody's looking at the side or in some strange direction, and the resolution is good, they're fairly close. But trust me, if you start to be far away, a bit blurry, etc., it's not an easy task. It's still not an easy task. And not just detection, because detection is one thing to understand, okay, there's a face, but to know who does this face belong to, that's another problem, right? And that is also, it's not easy, but it's being used right now. So I don't know how many of you have used Facebook's automatic tagging software, or let's say tagging option. Anybody? Yeah. Right, so you know that Facebook now can look at your picture and tell you who's in it, right? It's a bit scary, but it's in use today. And also smile detection, right? So let's say, for example, you want to take a picture and you want to know automatically which one was the good one, right? If you're taking a picture of your son and you took 10 of them, you want to just throw away all the ones where he wasn't smiling and just keep the nice ones. This you can already do. It's already in some cameras today. Another application is biometrics. So using vision to identify people, okay, and to re-identify people, to verify someone's identity. So does anybody know who this girl is? Has anybody seen this before? Anybody? Yeah? So for those of you who haven't, so this is a story of a girl who was caught up in the war in Afghanistan in the 80s. And a photographer took a very famous picture of her, okay, and ended up on the front page of National Geographic. So this same reporter, decades later, wanted to find this woman, a girl who's now a woman, and to understand, okay, what had happened with her life. But, you know, it was not easy to find her, okay? And then when he finally found someone who claimed to be her, he couldn't be sure, right? She looked so different. So what they did is they used iris matching technology. They took a picture of her eyes because her eyes were quite unique and they were also very high resolution. Okay, so it didn't have a picture of her fingerprint, but they had a picture of her eyes. And they used this same picture to match then a picture that they took of her later. And so they used this type of technology just to match the irises. And this is something that is used for identification for biometrics much beyond this, right? For other security systems. Right? And also, of course, everybody is familiar with fingerprints. And now, you know, many of you may have already used smartphones or things like this or laptops that have fingerprint readers. That is computer vision. Another one that is very wide use today is optical character recognition. Anybody heard of this before? Yeah? Exactly. So if any of you have used a scan at any point in time or anything that goes from speech to text or anything like this, then you'll be familiar with OCR. So the idea here is basically you have an image and from this image you can read it, right? You being, I mean the computer. It's done automatically. So for example, there are many cities around the world, many countries that use this, for example, for ticketing people, right? So let's say you're on the highway and you're speeding and you need to get a speed ticket. Rather than have a poor police officer chasing after you with his car, what people do now, what cities do now, states do now, is they simply have cameras around that take pictures of you, take pictures of the license plate, and because the license plate, of course, is registered, it's automatically read by a machine, the license plate number, and your ticket is sent right to your home, right? Also in toys and robots. So this is being used more and more. There are many toys are being developed, for example, for educational purposes, to interact with kids and things like this. And they all need to understand human interactions. They need to understand obstacles. They need to be able to move around and not knock into things. And all of this requires computer vision. And you know, even robots, like some of the first very widely used robots today, like a Roomba. Has anybody heard of a Roomba before? Right? Right? So this uses computer vision, right? It uses it for obstacle detection, path planning, things like this. Another one that many of you might be familiar with is medical imaging. So medical imaging, so typically when you have you know, like MRI scans, CAT scans, and other types of medical images, you know, you need to have a human being who spent many years being trained to understand and analyze and diagnose things based on these images, right? Which is very costly, and it results in a lot of delays, for example, in medical diagnoses. So what computer vision aims to do, and this is in use in some cases for certain types of pathologies, is to automatically analyze some of this imagery, right? So be able to say, instead of having a human poring over 10 different scans of someone's brain, you can input this image into a machine. The machine will automatically segment regions for you or detect regions for you. For example, you want to detect, a brain tumor. You give it to the computer nicely segments it out for you and then gives it to the doctor. And the doctor can now, instead of having to spend all its time laboriously, lining it by hand, this is done by a machine. And then the doctor can spend more time trying to understand the diagnosis, trying to speak to the patient, for example, instead of spending time doing this. Also in sports analysis. Is anybody here a tennis fan? Lawn tennis? Anybody? So any of you who have watched tennis will know that these days, players, if they're not happy with the result, they can ask for a review, right? And then somebody will play something like this, and you will say, okay, whether it's in or out. This is done with computer vision, okay? And this is used. There's a company called Hawkeye which sells this to many types of many sports fields. Another application is once again for robotics, right? In this case specifically for space exploration. So I don't know how many of you are familiar with the Mars rover. So this was a rover that went to Mars. And their computer vision is critical, right? So it needs eyes, right, to see, to move about, etc. So it needed it for panorama stitching. So you have a robot that's looking around, and you want it to have a continuous view of the scene, right? So I can look around, and I can immediately stitch the images that I see to form one coherent picture. But for a machine to do this, you need something which is called panorama stitching, which most of you might be familiar with if you've used a phone, and you take all these pictures, and then you get one nice picture. So this is, once again, computer vision. Also, once again, 3D, right? Terrain modeling, understanding, is there a bump in front of me? Should I move around? These types of things require vision. Also, as I said, for optical detection. Also for position tracking. So one of the things, so when we are in an environment, very often we can understand where we're moving, not just from the physical action of motion, but also from looking around us, right? So basically, if I'm here and I stand here, I have a lot of visual cues that tell me, okay, now I'm a bit closer, so I have a sense of how I'm moving. And vision is used a lot for robotics to do the same thing, okay? To understand not just, okay, I've moved, but really by how much. And you can use visual landmarks to tell you that. And that's what this robot does as well, or did. So one thing which is very trendy and which is like really leading to a huge boom in computer vision and interest is autonomous driving, self-driving cars. How many of you are familiar with this field? Yeah? Okay, good. So here I'm going to show you.
Rear-end collisions are one of the most...
So this is in production right now. This is a very well-known Israeli company that works in computer vision for driving assistance.
Common accidents caused by driver inattention. The mobilized system continuously scans the area in front of your vehicle,
you see it's detecting the lane,
all types of vehicles in your path,
detecting
including motorcycles.
distance.
The system calculates the relative speed and, in critical situations, issues both a visual and auditory warning of an impending collision with the vehicle ahead. The system can provide a warning of up to 2.7 seconds before impact, both during city and highway driving. Mobileye, our vision, your safety.
Their vision, right? So their vision is computer vision.
Unintended lane departure is the leading cause of serious accidents. A fatal collision can occur within a split second. The mobilized system is able to detect lane markings and can identify when your vehicle departs from its driving lane.
All of this detection is computer vision.
The mobilized system recognizes when the vehicle begins to drift from its lane without the use of the turn signal and issues an immediate visual and auditory warning, prompting the driver to return focus to the wheel.
So the world's worst driver, but yes. Okay, another application, this is one that I personally worked on when I was at Xerox, is computer vision for retail. So the idea here is that, let's say you're in a retail environment and you want to be able to understand your environment, right? So why might this be interesting? So one particular application that we were interested in at Xerox was in what we call planogram compliance. So what that means is that Many brands, so many companies that produce like products, supermarket products, grocery products, they pay for certain types of product placement. Okay, so basically, let's say you're Lay's chips, and you want to ensure that your products are placed with a certain configuration. People pay money for that. Okay, but because they pay money for that, they need to make sure that it's being done correctly. So what people do right now is that Lay's chips, or whoever manufactures Lay's, will pay somebody to go in, to take pictures of the store shelves, and to audit it, to compare it to something else, and to say, okay, this is correct, or it's not correct, okay? That's a lot of work. It's very expensive. So a lot of work is being done, and solutions are existing in the market today to do that automatically, right? To let a computer tell you where everything is, and is it compliant or not. So here I'll show you a small demo that we did using computer vision. So this was with a smartphone to recognize certain products, right? And you see it's recognizing it from different angles. So it has to see from the side, because you can imagine you have a shelf that's not very well organized. And so it's recognizing different products. Okay, so that's one other application. Another one that's very trendy right now, which a lot of buzz. Yes, sorry. So it depends. So I'm not sure what Amazon uses. A lot of apps use barcodes. So barcodes are another type of, let's say, computer vision, but it's a very simple signal, right? So it's a signal that you can read very easily. So I'm not sure if Amazon's using this. It's quite possible they do. If they tell you the barcode, then of course they're using it. If they just ask you to take a picture, then they're not. But I'm not sure. I'm not so familiar with this one. Yeah. So how many of you are familiar with mixed reality, augmented reality? Anybody? Okay, good. So then you're familiar with things like Gear VR, which are headsets for virtual reality. And this uses a lot of computer vision. I mean, it's almost 100% computer vision, right? Also for medical rehabilitation. So you might ask yourself, how is it used for medical rehabilitation? Well, so I know a company very personally. Actually, my husband works there. And so this company is involved in helping people who are recovering from some sort of like brain trauma. It could be a stroke and other things. And they need to do physical therapy, right? So very often this involves a physical therapist sitting down with you for an hour and having you do small exercises, right? Like moving your arm out and in, or different things like that, okay? And the physical therapist will tell you if you're doing it okay, giving you encouragement, like please do push a bit harder, go a bit, extend your arm a bit further. And this takes a lot of time. It's very expensive, and a lot of people don't get all the physical therapy they need because they simply don't have enough practitioners, right? Enough time to do it. So what this company aims to do, and there are several companies that are doing this, is to have a game do this for you. Okay? So basically, instead of interacting with a therapist, you're interacting with almost a video game, and this video game can give you encouragement, can see if you're doing it well, tell you how to do it better. But for a game engine to do this, the engine needs to understand how you're doing it, right? It needs to see you. It needs to understand the pose, where are all your limbs. It needs to know that can you extend your arm further or not. So this all involves what we call pose estimation and tracking. So this is HoloLens. This is me playing around with the HoloLens very recently. So of course you're not seeing anything. I look very silly just there with this HoloLens on. But what I'm seeing is an astronaut that's in the air that's just above me, and I can interact with it, move around, see where it is, etc. And so now for a nicer video. This is also of HoloLens.
Microsoft HoloLens brings holograms into your real world. Using transparent lenses, spatial sound, and an understanding of your environment, holograms look and sound like they're actually part of the world around you. That is mixed reality. With Microsoft HoloLens, holograms are viewed through the holographic frame centered in the middle of your view. This preserves your peripheral vision so you can move freely and connect and collaborate with people around you. Holograms in mixed reality don't block out what you can see and hear. This enables you to engage with digital content and tools alongside the objects in your real world. Holograms can be world-locked in a physical location, so you can walk around them, or they can travel with you. You can even hear them in 3D with spatial sound. Microsoft HoloLens is the world's first fully untethered, self-contained holographic computer. With the mixed reality experience of HoloLens, you can stay in the real world and interact with real people as you simultaneously explore 3D in 3D.
So you might ask yourself, okay, how is computer vision involved there? Right? Let me try to see if I can bring it in to a different point. I'll try to bring it in a second. So basically, computer vision there is needed. It involves everything, right? So let's say, for example, you have a machine and you want to superimpose this virtual object into your living room, okay? It needs to understand depth. It needs to understand how far are you from the supposed virtual object, right? So if you put the virtual object here in your 3D world, in your real world, you need to understand how big is the world, where am I in relation to the world. If I move further away from this object, it should change, right? It should look further. If I go closer, it should be closer. It needs to understand all of these things, and it can only do that by analyzing the feed, the video feed on top of this HoloLens, okay? So this is my last example, I believe, and so this is about really interacting with your environment, interacting with your world using vision. And this is from a recent conference that Google gave. So Google gives a conference every year. It's called Google I/O, where the CEO, who you'll see in a second, he discusses new technology that they're very enthusiastic about, right? And this year was really the year of computer vision, and you'll see it in a second.
Today, we are announcing a new initiative called Google Lens. Google Lens is a set of vision-based computing capabilities that can understand what you're looking at and help you take action based on that information. We'll ship it first in Google Assistant and Photos, and it'll come to other products. So how does it work? So for example, if you run into something and you want to know what it is, say a flower, you can invoke Google Lens from your assistant, point your phone at it, and we can tell you what flower it is. It's great for someone like me with allergies. Or if you've ever been at a friend's place and you've crawled under a desk just to get the username and password from a Wi-Fi router, you can point your phone at it.
That was very exciting for people. But this is OCR, as you see, right?
And we can automatically do the hard work for you. Or if you're walking in a street downtown and you see a set of restaurants across you, you can point your phone. Because we know where you are and we have our knowledge graph and we know what you're looking at, we can give you the right information in a meaningful way. As you can see, we are beginning to understand images and videos. All of Google was built because we started understanding text and web pages. So the fact that computers can understand images and videos has profound implications for our core mission.
Okay, so that's Google saying that now they're moving from understanding text, which was their bread and butter, to understanding images. And with that, it opens a whole new world for all of us to understand the world around us, right? And people who don't have good vision, who are vision impaired, but just you and me, right? Every day, as they say, going around the world and being able to use your smartphone and automatically get information about anything that you see. A flower you see, a movie you see, a building you see. Just imagine being able to extract all that information using vision. That's where we're heading. So those are the applications, and now I want to show you some of the challenges that remain, right? Because computer vision is really far from solved. So computer vision, as we've seen before, it's very powerful, it works quite well, but there are many cases where it doesn't work, and it's actually very easy to trick some computer vision algorithms, especially in ways that seem completely unintuitive to you and me, right? So to give an example, so to show this, some research was done at an academic institution to really understand how can you fool a computer vision algorithm when that is trained to recognize certain objects, okay? So what was done was a computer vision algorithm was given these images, right? So a bus, a school bus, some kind of bird, a temple, And the computer vision algorithm was supposed to recognize it, right? Give you an answer, what's in it. And the computer vision algorithm did quite well, right? It said, this is a school bus, this is some type of bird, this is a temple, okay? So what happens if you corrupt this image with some kind of noise, okay? So this noise is it's somewhat structured, but it looks pretty random to you and me, okay? So what they did, they took this image, they corrupted it or distorted it with this noise, and this was the resultant image, okay? So this image, to you and me, doesn't look any different, right? You would all say it's basically the same image, okay? But to a computer vision algorithm, that looks completely different. And it gives you, in this case, this image, this noise, distortion, was structured to fool it, to trick it into seeing an ostrich. So after that, the same algorithm, right, started saying, okay, no, this is an ostrich, this is an ostrich, this is an ostrich, okay? So that means that if you understand, let's say you have a computer vision algorithm, you can almost hack it or you can compromise it by saying, okay, I know exactly what type of image I need to show it or add to it to make it think it's something completely different, okay? So this is something that's not completely solved yet, it's not really understood, and this is an active area of research. Another one, anybody saw these? Who remembers this? Right, okay. So this was actually a problem for humans, right? The problem is which one's a chihuahua and which one's a muffin, right? I had to take up time looking at a few of these. But I don't think any of us would confuse a chihuahua for a muffin, okay? It might take a few seconds, but I think we could figure it out. So actually, a computer vision scientist asked himself, I wonder how a computer vision algorithm would do. And actually, it did not do badly at all. I was actually quite impressed, okay? In most cases, it was able to say it was a chihuahua or a muffin. I made two mistakes. One was this one, which is fairly understandable, okay? It said it was a chocolate chip cookie. But then it said that this was a blueberry, these were blueberry cupcakes. So you can understand, okay, they're similar, but I don't think any human would make that mistake. No? And then here's one other example. So let's say you have an autonomous driving system, a self-driving car, and it's seeing a picture in a picture, right? So this is a cyclist, yes, it's a person, but it's a sticker, right? So it's not an actual person. But, this is very difficult. This involves a different level of analysis, right? It goes beyond saying, okay, I'm seeing a person, but you need to understand it's a person in a picture, not an actual person, right? So this is also not trivial. So I don't know if any of you have been following up with Uber. Are you familiar with Uber? Right, so you might know that they're making a very big push right now for self-driving cars, and they're doing tests right now about this. And very recently, there was a bit of a scandal because they were testing their car in, I don't remember which city, and the car completely ran a red light, right? So it ran a red light in a situation where a human, unless you were absolutely not paying attention, would never run a red light, right? Because you imagine that this is not, this system is not distracted. It has many cameras. It has probably 8 cameras. It has a LiDAR on top of the car. It has all kinds of sensors. And there are at least 4 red lights in the scene, okay? And yet it still breaks it. So that means that the red light detection on this machine fails, right? In this situation that it would never fail for a human. And then also you have situations like this. Anybody heard about this? When Google decided this was a gorilla? Yeah, so Google very happily went out and released their image recognition application. Oh, we're so great. And it's very good. But when you make mistakes like this, it's very costly, right? It's very embarrassing and it's very costly. So yes, there's a lot more to be done. So those are the challenges. I'll finish with a brief conclusion. So as I said, pixels are everywhere. They're everywhere in our real lives and our digital lives. And I think I've convinced you, hopefully, that computer vision can aspect really every aspect of life in society, from medical imaging to rehabilitation to entertainment to simply just navigating your environment. Really, there's no aspect of life that I think computer vision cannot touch, okay? And really, this is why I think it will drive the next revolution in artificial intelligence, as it's doing right now with augmented reality, with self-driving cars, and really other aspects of innovation right now. And that's it. Thank you.